Helicopter flying. 2-1 Aerodynamics of flight. Let's discuss the forces acting on the aircraft. We're going to delve into the forces that come into play once a helicopter leaves the ground. These forces are crucial for understanding the dynamics of flight. Here is the explanation of forces. Lift. Lift opposes the downward force of weight. It's generated by the dynamic effect of the air acting on the airfoil and acts perpendicular to the flight path through the center of lift. Weight. Weight is the combined load of the aircraft, including the crew, fuel, and cargo. It pulls the aircraft downward due to the force of gravity, opposing lift, and acting vertically downward through the aircraft's center of gravity. Thrust. Thrust is the force produced by the power plant, whether it's a propeller or rotor. It opposes or overcomes the force of drag. Generally, it acts parallel to the longitudinal axis, but there are exceptions, as we'll discuss later. Drag. Drag is a rearward, retarding force caused by the disruption of airflow by various aircraft parts like wings, rotors, fuselage, and protruding objects. It opposes thrust and acts rearward parallel to the relative wind. It's essential to grasp how these forces work and to master the use of power and flight controls for effective control during flight. What is lift? We're unraveling the intricacies of lift, the force that defies gravity and keeps aircraft soaring through the skies. So, buckle up for a journey into the forces of flight. Fundamentals of lift. You see, lift comes into play when an object changes the flow of a fluid, like air. It doesn't matter if the object is moving through a stationary fluid or if the fluid is streaming past a stationary object. The principle stays the same. It's all about the viewer's frame of reference. Factors influencing lift. Speed of the airflow. The speed at which air moves is a critical factor in generating lift. Density of the air. Air density, influenced by factors like altitude, has a direct impact on lift. Total area of the airfoil. The size and shape of the airfoil, or the rotor blade for helicopters, contribute significantly to lift. Angle of attack. Now, angle of attack, or the angle between the airfoil and the oncoming airflow, is a game changer. It determines the magnitude of lift. Angle of attack and lift in helicopters. In the world of helicopters, the rotor blade is our airfoil, and the air is our fluid. Positive lift happens when we deflect the mass of air, always acting perpendicular to the resultant relative wind. For symmetric airfoils, you need a positive angle of attack for positive lift. No angle of attack means no lift, and a negative angle of attack generates negative lift. However, with cambered or non-symmetrical airfoils, you might get positive lift even at zero or slightly negative angle of attack. Complex interactions. Lift may sound simple, but the dance between air and airfoil is complex. Whether it's an angled flat plate, revolving cylinder, or airfoil, the flow meeting the leading edge is forced to split over and under the object. This creates a sudden change in direction over the object, forming a low pressure area behind the leading edge on the upper surface. Due to pressure gradient and fluid viscosity, the flow over the object accelerates down along the upper surface, while the flow underneath is slowed, causing a high pressure area. This dynamic duo produces lift as the fluid sections leave the trailing edge with a downward component of momentum. Understanding this dance is the key to unraveling the mysteries of lift and ensuring the graceful flight of aircraft. Understanding Bernoulli's principle. Unraveling the aerodynamic. Ever wondered why an airfoil develops an aerodynamic force? Bernoulli's principle holds the key to this phenomenon. Let's dive into the relationship between internal fluid pressure and fluid velocity, uncovering the secrets behind this principle. Principle overview. Bernoulli's principle is essentially a statement of the law of conservation of energy. It sheds light on the relationship between internal fluid pressure and fluid velocity, providing insights into the development of aerodynamic forces. The law of conservation of energy asserts that energy cannot be created or destroyed. In this context, the energy refers to dynamic pressure, kinetic energy of the air, and static air pressure, potential energy. Although these energies may change, the total pressure energy within the system remains constant. Illustrating the principle. A simple tube with a constricted portion near its center, like water flowing through a garden hose. The mass flow rate, mass of flow per unit area, remains constant. If the cross-sectional area at any point in the tube is reduced, the fluid velocity must increase to maintain a constant mass flow rate. The continuity of mass flow causes the air to move faster through the constricted portion, known as the Venturi effect. Venturi effect and Bernoulli's equation. Bernoulli's equation. Total equals P dynamic plus P static, explains that the increase in velocity results in an increase in streamwise dynamic pressure. To maintain total pressure, static pressure on the sides of the constricted portion decreases. This phenomenon is known as the Venturi effect. Figure illustrates the dynamic flow and static pressure on plates within the tube, showcasing the corresponding pressure changes. The reduction in static pressure on the sides of the Venturi, particularly at the top, is crucial in understanding aerodynamics. Application to airfoils. Applying this principle to airfoils, consider an imaginary point, point 2, where static pressure reduction on the top of the airfoil is visualized compared to the bottom, ambient static pressure. The actual aerodynamics of blades involve complexities like design and angle, but the core idea remains: static pressure differential generates aerodynamic force. Bernoulli's principle unravels the aerodynamic magic behind airfoil lift generation. Understanding the interplay of dynamic and static pressures provides a foundation for comprehending the forces that keep aircraft soaring through the skies. Venturi flow. Unveiling the dynamics top of form. Let's dive into the fascinating world of Venturi flow, where the principles of fluid dynamics come alive. This phenomenon occurs within a closed system, like a tube, and plays a crucial role in understanding how pressure and velocity interact. Total energy and pressure in flow. Within a closed system, the total energy remains constant, but its form can be altered. Consider the pressure of flowing air as a form of energy. The total pressure of flowing air stays constant unless energy is added or removed. Components of fluid flow pressure. Fluid flow pressure is comprised of two components: static and dynamic pressure. Static pressure. This is the pressure component measured in the flow but not moving with it. It's the force per unit area acting on a surface. Dynamic pressure. This component arises from the movement of the air. The sum of these pressures results in the total pressure. How pressure changes in Venturi flow. As air flows through a constriction, static pressure decreases due to increased velocity. This reduction in static pressure leads to an increase in dynamic pressure. Even with the removal of the top half of the tube, air continues to accelerate over the curved area. This acceleration is akin to what happens over the top half of the constricted tube. The upper air layers restrict the flow, causing acceleration and decreased static pressure above the curved portion. This sets the stage for a pressure differential created by the interplay of static and dynamic pressures. Newton's third law of motion in helicopter lift. Let's explore how Newton's third law of motion plays a pivotal role in understanding the additional lift generated by a helicopter rotor blade's lower surface. This phenomenon involves the deflection of air, creating a lifting reaction according to Newton's timeless law. Newton's third law. Newton's third law of motion states that for every action, there is an equal and opposite reaction. In the context of helicopter lift, when air striking the underside of the rotor blade is deflected downward, it results in an upward, lifting, reaction. Let's discuss the following factors. Comparison to water skis. To grasp this concept, think of air behaving like water. The explanation parallels the planing effect of skis on water. The lift supporting water skis, and the skier, arises from the impact pressure and deflection of water from the lower surfaces of the skis. Application to rotor blades. Similarly, in helicopters, the lower surface of the rotor blade deflects air downward, creating lift as a reaction. This is in accordance with Newton's third law. Magnitude of lift contribution. Under typical flying conditions, it's important to note that the impact pressure and deflection of air from the lower surface of the rotor blade contribute to a relatively small percentage of the total lift. The primary source of lift is the result of decreased pressure above the blade, rather than increased pressure below it. Newton's third law of motion beautifully explains how the deflection of air from the lower surface of the rotor blade creates an equal and opposite lifting reaction. While this additional lift is a fascinating aspect of helicopter aerodynamics, the lion's share of lift still stems from the decreased pressure above the rotor blade. It's a delicate dance of forces that keeps helicopters soaring through the skies. Unlocking helicopter weight dynamics. Weight, a critical force in helicopter flight, is more than a fixed value. Delve into the intricacies of weight and its influence on the lift needed for a helicopter to take off. Newton's first law and lift. Newton's first law dictates that an external force is needed to alter an object's state of motion. Lift, achieved by increasing the pitch angle of the main rotor blades, becomes this force, allowing the helicopter to ascend vertically. Aerodynamic loads and load factor. Banking a helicopter increases the load factor or G load. This factor, the actual load on rotor blades divided by gross weight, rises during maneuvers. Tighter turns or rapid maneuvers amplify the load factor. Impact of load factor on lift. To counter increased load factors, the helicopter must generate more lift. Limited engine power may lead to descent or deceleration to maintain altitude. Rotor blade distribution and limitations. Rotor blades distribute the load, with each blade carrying a percentage of the gross weight. Helicopters have limitations based on their structure, size, and capabilities. Pilots must avoid exceeding the helicopter's performance envelope. Understanding the helicopter's capabilities and staying within the flight envelope ensures safe and controlled flight. Mastery lies in anticipating the effects of maneuvers and embracing a disciplined approach to flight. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.